Everybody, welcome to video number 3 on topic 1.3, finding limits graphically. And in this video, we're going to be talking about when limits fail to exist. And we've already seen a couple of these before, and we know that in order for a limit to exist at a specific value, the left-hand and the right-hand limits have to exist, and they have to be equal. So let's look at 4 conditions when a limit fails to exist. And number 1, and probably, in my opinion, one of the most common, is that the one-sided limits are not equal. And so if we look at the unequal one-sided limits here, you can see if we're approaching 3, because they're asking us down here, hey, explain why the limit doesn't exist at 3. Well, from the right, I approach 1 with my limits, my output value, and from the left, I approach 2. The left-hand and the right-hand limits don't match. So as x approaches 3 from the left, that does not equal the limit as x approaches 3 from the right. Therefore, the limit at 3 does not exist. In number 2, the function doesn't approach a finite value. Now, here from the right, we approached 1 in the first example, and from the left, we approached 2, specific values. But if you look at these infinite limits, and you could say, well, from the left, Mr. Bennett, I'm going to infinity. From the right, I'm also going to infinity. So the limit at 2 is infinity. And that's true. But it's not a specific value, so technically, the limit does not exist. And so it just depends on the author of what they're going to put in the text. So the limit here of both from the right and from the left are both equal. They both go to infinity, but that's not a specific number, so therefore technically that limit does not exist. Now it's okay to put the limit as x approaches 2 is infinity, that's fine, but really it does not exist. 3 sounds an awful lot like number 2. The function does not approach a particular or specific value. And not a finite value, a specific value, meaning it can't lock in, and that's the infinite oscillations. And you can see here, if I go in, it's going to ping pong back and forth. It just goes back and forth, back and forth. It can't lock in on a specific value. You can't locate it. Later on, you'll learn about the squeeze theorem to try to help you find these, but if you can't lock in on a specific value, the limit's not going to exist, because explain why this limit doesn't exist. You know, we can't determine that y value. The function is behaving so erratically there, it's just going back and forth super fast, we can't lock in on it. It might, you know, at one number, as we get close to a number, and then as we get closer to, like, let's say 1, if we're at 1.5, we lock in a number, but all of a sudden 1.25, it's down here, 1.1, it's up here, 1.001, it's down. It just keeps ricocheting back and forth. We really just don't know what number that's approaching. And finally, the last one here, the x value is approaching an endpoint. So if we look at the limit here, as x approaches 1, yeah, it's an endpoint. We only have the right-handed limit. So as we approach 1, so we know that the limit as x approaches 1 from the right exists. Okay, it's 1. Well, what about that left-hand limit? So that left-hand limit would also have to approach 1 in order for our limit to exist there, but we don't know. There's no graph there. Where is the graph? Is it up here? Is it over here? We don't know. So we can't make a guess on what the left-hand limit's approaching. Therefore, the limit does not exist because we don't have, in this case, a left-handed limit. So that's it for the when do limits fail to exist. Remember, there are 4 cases. So if you have any questions or comments, please feel free to leave them below. And we'll see you next time for topic 1.4, finding limits from tables.